so here we go. So today, we're going to utilize everything we've learned so far in gases and stoichiometry to do a really fun lab. It's called the H2 Pop Lab. Now, just like last time with the gassy lab, we're going to do water displacement. But unlike last time, we're actually going to do a chemical reaction to produce the gas. And the gas we're going to produce is hydrogen gas. Is hydrogen gas less dense or more dense than air? Hydrogen gas has a molar mass of 2, H2. So it's less dense or more dense than air? Less. Remember air's magic number? 29. Okay. Oxygen's is 32. Nitrogen is 28. A lot of you got that wrong on the quiz. Don't get it wrong on the retake, please. So 29. If something is less dense than 29, lower molar mass, it will rise or fall?
Rise.
It will rise. And if something is more dense than 29, it will sink. Okay. So there was a couple exercises that said, which of these gases is going to sink in air? Which of these gases are going to rise in air? 29 is your magic number. Okay, so back to the lab. So hydrogen's got a molar mass of 2. What we're going to do is we're going to take some 1 molar hydrochloric acid, the hydrochloric acid from these guys. Okay? Don't grab AP Chem's hydrochloric acid because they're not concentrated enough. Okay? So 1 molar hydrochloric acid, and we're going to put a piece of magnesium. Okay? Magnesium loves to react with hydrochloric acid, and when it does, it makes hydrogen gas and magnesium chloride. Hey, is this a balanced chemical reaction?
No.
Can we balance it?
Yes.
How might we balance it?
Add a 2 to HCl.
Add a 2 to the HCl?
Yeah.
And then we got 1 magnesium, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. Sounds good. Okay, so what you're going to do, practically speaking, is you're going to put some magnesium into some hydrochloric acid. It's going to produce gas, which we're going to capture in this crazy little gas collection device. We have an Erlenmeyer flask with a 1-hole stopper, and on that 1-hole stopper is a piece of glass tubing, and that glass tubing is connected to some tubing, rubber tubing, and the rubber tubing goes under the graduated cylinder. In the water. So previously where we put the little gas canister under the graduated cylinder, now we're going to put the gas tube under the graduated cylinder like so, and bubbles is going to be coming up. Make sense?
Yes.
Water displacement again, just like before. So what are you doing in the lab? Well, you're going to use Pipner, once again, just like before. Pressure is going to be a nice 1.0 atmospheres because it's a nice sunny day. And R is going to be once again 0.0821 because we're using atmospheres. T is going to be the Celsius plus 273. The Celsius is going to come from your thermometer. Just like before, nothing much has changed there. In this lab, however, what we want to do is we want to figure out volume. We want to figure out experimental volume. And we're going to figure out the experimental volume by finding the experimental moles. Okay. Does this make sense so far? We want to figure out the volume, the ideal volume of hydrogen gas by figuring out the ideal volume, the ideal moles of hydrogen gas. And to do that, we're going to use stoichiometry. We're going to weigh our piece of magnesium. And our piece of magnesium is going to give you grams of magnesium. We're going to use a T-chart to find eventually moles of hydrogen gas. It's probably not going to be that long. Probably just 2 boxes. Okay. So moles of hydrogen gas. And where's the moles of hydrogen gas we get from this equation going to go?
Into the N.
Into the N, exactly. This is going to be N. So we're going to do some stoichiometry. We're going to start with grams of magnesium. We're going to get to moles of H2. That moles of H2 is going to be our N in Pivnert. And then that N is going to give us V. And we'll have our ideal volume. Ideal volume. Not experimental volume. Then we're going to do a percent once again, just like before. Percent error percent error is once again going to be the ideal volume minus the experimental volume over the ideal volume, absolute value times 100. Want to see it happen? Okay, so digest that while the magic happens. So once again, I'm going to try to do this single-handedly. It's not easy. You're just going to fill up your Erlenmeyer flask to 125 milliliters. There we go. You're going to get your zinc, you're going to get your magnesium, you're going to weigh your magnesium. Now ideally, your magnesium should be somewhere between 0.08 and 0.12. Mine is 0.124. So it's a little too heavy. I'm going to crack off the bottom and then weigh it again so it doesn't exceed 0.12. All right, now I'm at 0.11, which is perfect. So if your piece of magnesium is bigger than 0.12, break it. If it's smaller than 0.08, add more. You can use more than one piece. Does that make sense?
Yeah.
That window is important because if you exceed that window, you're going to exceed the volume capacity of your graduated cylinder. And if you don't have enough, you'll be like, I got 45 milliliters, which isn't going to be very fun. Now, next, your graduated cylinders are graduated from 0 to 100. Beyond that, you can just estimate. You could be like, it got down to here. It looks like 100 plus maybe 15 milliliters more. Make sense? So I'm going to say the upper limit of our graduated cylinders, 130. Cool? All right, so water displacement, dunk it, fill it up, and then you're going to, hopefully one person does each thing. Okay. So you're going to put the magnesium in the flask and capture the gas. And now we're passing a mass of gas through a glass in class again. Yay! But we're not going to worry about the mass of the gas that we pass through the glass in class. You can shake it if you want to speed the reaction up a little bit. You can kind of swirl it. Doesn't really make a huge deal because the bubbles are all up in the thing. But now, we don't care about the mass of the gas that we're passing through the glass in class. We care about the volume of the mass of the gas that we're passing through the glass in class. So again, I measured out my magnesium to be about 0.11, so I should not exceed 130 milliliters. I should come awfully close though.
It's the error percentage.
It reacts with it. So what's happening is the magnesium is reacting with the hydrochloric acid,
And we're making
magnesium chloride and hydrogen gas, which we are collecting in yonder tube.
Why is it called pop lab?
Not at all. Question?
Why is it called pop lab?
That's a good question. So the question in the back was, why is it called the pop lab? Okay, so my magnesium is now gone, and I'm not making any more gas. So I look at the line. I made 100, probably plus another, by weird coincidence, 15 milliliters. So I made about 115 milliliters of gas. This is my experimental volume, 115 milliliters, which before I put into Pivnert, I'm going to convert to liters, exactly. So Pivnert needs liters. I'm going to turn my 115 milliliters into 0.115 liters. Okay, now, why is it called the pop lab? It's called the pop lab because this next step is fun, but totally optional. So what you do is, okay, first of all, hydrogen, more dense than air or less dense than air?
Less dense.
Less dense, so it's going to
Rise.
okay? So I'm going to pour out some water, let the water go, okay? And now I got my hydrogen in here, and a lot of water vapor. I'm going to select my favorite aim and flame. Again, this part is totally optional. And then, I'm going to bring my aim and flame and my hydrogen gas over to the designated popping area. This is the designated popping area. No one's doing lab over here. And you're going to get your flame, then you're going to invert your graduated cylinder to allow the hydrogen gas to escape into the flame. Sound like fun?
Yeah.
All right, so get my flame first.
Oh, that's cool.
That's why it's called the pop lab. Cool? Some of you are going to get a puff, and some of you are going to get a pow! So, you know. Okay, questions? From the top. You're going to need your water bath, your gas collection tube, an Erlenmeyer flask, which are over there in the cabinet. Graduated cylinders are right there, acids are right here. If these run out, let me know. I've intentionally let them low volumes, like you still about to go, and temperature thermometer in the water bath, then you're gonna need 4 pieces of magnesium between 0.08 and 0.12 grams. And those are right there. Questions? Okay. Are you gonna wear glasses?
Yes.
Yes. Are you gonna tie your hair back?
Yes.
Yes. All right. So get your lab group and off you go.